Am I audible? Okay. Am I audible in the back? Am I audible in the back now? Clear? Okay, great. So, what were we doing in the last class? Hmm? We looked at what a memory compiler is, and we looked at memory data sheet. And we also, in that, looked at what is the importance of mux inside a memory. So, what is a mux and why is it important? Hmm? So, the physical dimensions of a memory can be very cigar like or very horizontal or very tall, whichever way you want to look at it. And that may not be feasible to be included inside the SOC. It will completely disorient the shape of the design that we are working on. And additionally, there would be some RCs which could be very, very long and can lead to a large delay. So, two reasons. First, that we need to have an aspect ratio which is usable in the context of the design that I'm working on. Second, the performance would go for a toss if RCs are very, very large because it's a very long line that we are running. So it is desirable to fold the memory by using what we call as multiplexers. So we have multiplexers on the outputs and we have multiplexers on the inputs, which would ensure that uh, even if there are more than one words written per row, we are still able to read only one. And we are able to select one word into which we will write when we are trying to write from the IO side. Is this clear? We also very briefly looked at the fact that when you change the mux, so timing to humne, we started the timing will change, but we also expect to a change in power because now more number of bit lines will discharge. There are more bit lines per word line and more of them will discharge. So the power will also change. So it is not just about aspect ratio or improvement of timings. There could be some change in power also, and we need to look at it. We cannot just simply decide that this is what my mux is going to be. We have to look at the entire PPA of the system there. We also looked at the data sheet there, and we saw that depending on my design and depending on the mux, the step size between words could vary. If it is mux 4 and I can increment one row per in one time, then my words will increase by step size of. I'm saying an increment of one row is possible and my mux is 4. What would be the step size of my compiler? 4. If only two rows can be incremented, one row is not even allowed to be incremented, then what is the step size? Now, if with this kind of a constraint, if the mux is 8, what is the step size? 16. Is this clear? So, what we also looked at in the last class was that while this course is being called memory design course, and we will talk only about memory design, that is not exactly what you will be doing when you join the industry. When you join any memory group in any company, what you will essentially be working on is what is called as a memory compiler. How is a memory compiler different from a memory instance? It enables a user to generate a very large number of instances according to their requirement. Is that an automation tool kind of memory compiler? So again, software is a part of it. Software is a part of a memory compiler. But a memory compiler, as we discussed last time also, has the software, has a whole library of leaf cells, which will be used to create the memory instance that we want, has a characterization engine, which will be used to characterize, has a Verilog generation engine, which depending on your memory instance, the number of address pins will change, a datasheet generation engine, and a whole paraphernalia. It would generate all the MAT10 views. What is MAT10? It is not used in the lectures, I know this. What is MAT10? Okay, forget MAT10. If I ask you what is TRL3 or TRL4, what do you understand by this term TRL, this acronym TRL? Huh? क्या? ट्रांजिस्टर लॉजिक? किसने बोला ये हाथ तो खड़ा करो? ओके, व्हाट एल्स? नहीं नहीं पता तो तुक्का तो मारोगे यार. What could TRL stand for? How many of you have? Okay, अभी इस ग्रुप में there is no one who has done a BTP presentation yet. Uh, okay, what is TRL? हाँ? Okay, इसने करा हुआ है ना. इसने BTP करा हुआ है. TRL stands for Technology Readiness Level. And TRLs go from 1 to 9. Where at 1, we say we observed a technological concept. And at 9, we say that not only is the concept proven, the technology is actually ready to be industrialized. We built a product around it, we have verified it. So in between, you have the stage of what is called as a POC, which is at TRL 3. You will have a stage of a prototype, which will be TRL 4 or 5 or 6, depending on what is the maturity of your prototype. And you will do stuff like verification, what kind of environment and settings you have verified your IP in, your design in, all that. That is TRL 4, 5, 6. 7 is now we are starting to use at the customer end, launching it to the customer, collecting feedback from them and doing something. And TRL 9 is customer के feedback को भी include कर लिया. जो भी corner cases से कहीं कहीं पे fail हो सकता था, everything is proven, validated. This is now ready to go into mass production. That is what you do for technologies, okay, in regular parlance. In semiconductors, there is something which we call as maturity levels. Or MAT levels. And in businesses, the first stage that they recognize for a product is called as MAT 5. MAT 5 is a stage where the specification of your product is frozen. What is it that you want in your IP? What are the kind of timings that you want? What is the timeline in which you will deliver the IP? What are the kind of views that you will do? What is the uh, power consumption? What is the size of your macro, PPA, everything, timeline in which you will be committing, which views will come when, statement of work. ये क्या बातें कर रहे हो आप? See, when you are offering solutions, those solutions are meant for someone. Are they not? या अपने अपने ख्याली पुलाव बनाते रहोगे? Whatever you do, that solution is to be used by someone in the company or somewhere. Is it not? So the user tells na that I need this kind of maturity or I need these kind of views. I want that IR drop should be limited to only this much. I want the timing should be within this. Customer will tell na. When you go to purchase a phone in the market, there are multiple people who say that, okay, my phone, my phone, my phone, my phone. It is your choice. You tell that, okay, no, these are rejected because they don't even have a octa-core microprocessor. I want an octa-core one. These are rejected because they do not have a neural engine in it. Depending on कितना ऊंचा नाक है आपका, कुछ नहीं करना आपको उस न्यूरल इंजन से, but you may demand. So that agreement that you have with your customer that, okay, this is what I will deliver in this particular timeline is what is called as MAT 5. MAT 5 ke baad, there is another intermediate stage which we, at least in ST, used to call MAT 9. But what the user needs is MAT 10. Then there is something called MAT 20 and MAT 30. And then beyond that, MAT 40, etc. होते हैं, which are about a dying product. So what is MAT 10? पहले MAT 10 पे आते हैं, then we'll go to MAT 9. MAT 10 is a stage for an IP, जहां पे उस IP को अब SOC में integrate करा जा सकता है. It is a stage, it is a level of maturity in which any IP can be now integrated inside a SOC. All of you have done the RTL to GDS flow. What all did you need to go from that RTL to GDS flow? Let us just go one by one. What was the first few that you needed for? Suppose you had to use a NAND gate in your, suppose you were hardening a RISC-V core. Which designs did you harden in your VDF course? Project में करा था ना कुछ hardening, you must have done an RTL to GDS flow on something. Which design was that? Huh? It was some RISC-V core. So when you wanted, so you had an RTL of a RISC-V core, and then you said इस RTL को मैं GDS तक लेके जाने वाला हूँ. So what was the first thing that you needed after that? Some Verilog view of the NAND gates of everything. A netlist बना ना एक. Netlist में क्या था? Verilog netlist बना पहले. Verilog netlist में क्या था? It called an AND gate. It called an AY gate. It called a wide range of cells to implement the functionality that was desired in the RTL. After you did that, you did a functional simulation with Model Sim. I'm just refreshing VDF for you. And I'm not an expert in that, so I may go wrong. That you may have one or two extra steps in between, or just eaten away one step. I don't know. So once you did a Model Sim simulation, you saw functionality is fine. So what you needed in that first stage of validation was a functional model, a Verilog model of my design that, okay, when you trigger the clock, Q comes after this time, or when you take A and B both equal to 1, the output also rises to 1 in an AND gate. And there were unit delays that you talked about in the first simulation. First simulation was only about unit delays, functionality. Then you did the next simulation where you said, okay, now let me put the timing also. Unit se aap timing pe gaye. So what happened? Now the Verilog model also used the characteristics that were put in the .lib. Are you with me? Then once that was also qualified, you did all that correction, sab kuch. Then you said, okay, now let me go and do it on a layout. So वो layout के लिए आपने क्या करा? आपने उसको netlist generate करी and you started to do PNR around it. Now, what did you need in the PNR? You needed the dimensions X, Y of every cell and the location of the pins in those cells. You did not need to know the transistor sizes. Did you need to know? Did you ever find out what was the size of the driver of the NAND gate there? No, you do not know. But what do you know? Okay, this NAND gate, this is the size, X is this, Y is this, and the pins are at this location and that location. That was when the PNR tool could even place or route your cell. Are you with me? It did the entire PNR. Then at a much later stage, you brought in the layout so that you could now do DRC. Did you do DRC at the core level? Because GDS hai ye. So then you did DRC at a much later level. And once that was also done, you must have just done a sign off and said timing driven sign off kuch kara hoga, and you would have said, okay, jab tape out kar do. Something like this happened. Now come to think of it, what did you do in DVD? Wait, in DVD, did you generate any of these views except the layout view? Nothing, na? But you know that whatever AOI you made, that would go into RTL to GDS. So what happened? Who generated those views? Do you see a disconnect? You somehow jumped from what you did in DVD to VDS, but no one told you what happened in between. So something happened in between. No, characterization you did. You told me you did Monte Carlo also for power simulations, yeah. You did characterization. Which we have made in DVD, the RTL for the. So what you did not do was, so what you did was you created what are called as Mat9 views. You created a layout. You created a timing file. You created something which could, or a functionality के लिए आपने एक truth table बना दिया. That was what you did. These are Mat9 views. This is called as maturity 9. That the design side of this IP is done. Even the RISC-V core. Now, do you think the RISC-V core where you left it, someone could use it? No. To be able to use your RISC-V core, people need a symbol view. Did you create a symbol view of your RISC-V core? People need an abstract view. Did you create an abstract view of your RISC-V core? So that RISC-V core was also only at Mat9. Are you able to see this? Whatever you have done until now, that cannot be directly used in the SoC. Whether it was DVD, DVD वाला तो आप VDS में भी नहीं यूज कर सकते डायरेक्टली. जो आपने VDS में करा वो आप SoC डिजाइन में नहीं यूज कर सकते डायरेक्टली. So it's same thing. So all this design work that we're talking about is called as maturity 9. When you reach maturity 9, you've already fully verified your designs. You're fully verified, you're fully characterized also. All that part is taken care of. And when it comes to memory compilers, it is not one instance that you've done this for. You've done this for every possible instance that could be generated. Or you will not do for every possible instance. As we said, we will do some interpolation that, okay, 15-bit के कट को कर लिया तो उसके बाद 16 वाले को नहीं करेंगे. We will directly jump to something like, say, 50 and then interpolate the timings in between them. Something we would do. But what you are still claiming is that my design is clean, still not usable. So you need an engine to convert these Mat9 views into what are called as Mat10 views, where you have a symbol, where you have an abstract view, where you have timing.lib, you have a range of functional models, which could be used for scan insertion, which could be used for so many things that you do at your RTL to GDS flow levels. Are you with me? And that is when you get the maturity for your IP to be used in the designs. So all this for us will be done by the memory compiler level. So memory compiler is not just a software. So it's not just a software that does some tiling. Memory compiler is actually a Mat10 instance generation engine, where I did a Mat9 on the memory compiler, and then this engine goes in and says, okay, I know this is the timing for cut 1, this is the timing for cut 2. Let me generate that equation. You remember the equation that I showed in the data sheet that time? So the generator would generate that equation, or you will probably feed that equation into the generator so that whichever instance user asks for the timing of, it will not just create a data sheet, it will also create a .lib so that the users can use it. Are you with me? So again, I again want to give you that lesson in humility कि हम आपको जितना भी यहाँ पे अभी बता रहे हैं, that is only a small part. Don't fly on cloud nine कि मुझे तो सब कुछ आता है. Have the humility to realize there is so much more to learn. Those lectures, online lectures that you have, they are just showing you a glimpse. We are going a little deeper, a little broader over here. But this is also far away from what you will really need to learn when you join a company. So it is not for no reason that I've worked for 25 years in memory design. Na? There is so much to learn. Hmm? So keep that curiosity alive. This is extremely important today because information AI already has. The whys it doesn't have. Because it doesn't understand the whys, it can give wrong results very often. And semiconductor industry is such that where you cannot afford anything wrong. Are you with me? Because if you understand the whys, you will be able to use AI as your slave and stay put in your jobs. If you leave the whys behind, then आप भी mistakes करोगे, AI भी mistake करेगा, then AI is better. It will do lesser mistakes. So focus on understanding, focus on why something is needed, where something is needed, so that then you can use AI and automation to help you. AI and automation are definitely necessary. The kind of, the number of views, and तो भी गिराया भी नहीं आपको. You just create those designs, schematics, netlist, and layout, and some characterization timings, etc. And finally, you will see that a memory compiler will generate, or even a standard cell library would have 40 different views. Something runs with Cadence, another thing runs with Synopsys tools, another thing runs with another flow. Something is used in the DFT step, another thing is used in another step for something for best insertion, something for low power modes. So many views may be needed. And the engine does that for you. That is where automation is necessary, but आपको पता होना चाहिए. If needed, so when you join such a company, such a place, for example, if few of you wish to go for an internship at SCL, find out what is it about. Are you able to see this? Because these SCL type की जगह जहाँ पे automation अभी कम है. See, you go to Synopsys, ARM, Synopsys, let us say. Now, Synopsys is a CAD company, an EDA tool company. Is it not? पूरा Synopsys का flow आप use करते हो. They have a large number of computer science engineers working with them. They want to automate this. They can automate this in a manner that as a VLSI designer, you will not even know what is happening behind the scene. इतना सुंदर सा इंटरफेस देंगे, आप बस रोबोट की तरह पुश बटन करते रहोगे. But you go to a place like SCL, क्या सर गवर्नमेंट कहाँ भेज रहे हो? तो स्टाइपेंड भी नहीं देते. Okay, they don't give stipend, but what do they give you? They actually give you a hands-on experience to work on Mat9 views and convert them to Mat10 views and all the other nitty-gritties that you will not ever get to see at Synopsys. The under the hood things. Are you able to see this? So only when you understand the under the hood things, you will be able to create something of your own. Na? So choose wisely. जब भी आपको अंडर द हुड कुछ देखने का मौका मिल रहा है, नेवर लूज दैट अपॉर्चुनिटी. Because more and more with AI, you will not get to see this. Are you with me? So a memory compiler is not just a software. It's a software plus all the Mat9 views so that a Mat10 view can be generated for the user. Is this clear? So खाली software नहीं है compiler. Compiler is That software plus all the Mat9 views. That is what you call a compiler. Is this clear? Any other questions? अब वो कहेगा मैंने क्यों पूछ लिया memory compiler? मैंने software क्यों बोल दिया? Sir कहाँ ले गए? But no, that's see, do you realize that is how you are creating this class? The questions that you ask will bring out something else in the discussion. Something new will be unraveled. So you have, if you don't interact, then the lectures are already recorded and available there. But when you interact, when you ask questions, you will get to know, learn more things. That is why you are here now, to learn more things.
This is concept of standard load. So it's a standard load like just a constant or something that is calculated from the design itself.
Good. So when it comes to characterizing timings, one team, suppose now, okay, the way our industry is organized, there could be a standard cell team working in Noida, another one working in Bangalore, someone working in Israel, someone working in UK, and then US and Korea and all the places. Depending on which company you are, there could be teams working across many, many places. Now, in the Noida team, let us say Madhav is the manager. Madhav कहता है कि I think a typical user will have an output load of 5 femtofarads. So all the characterizations that we should do are at 5 femtofarads. That is based on what Madhav has experienced. At another place, let us say Yash is the manager. Okay. And Yash says that, oh, I have designed memory row decoders, I have designed big circuits, and I know that the load is going to be 25 femtofarads. So his team starts to characterize timings at 25 femtofarads. At another place, let us say someone else is the manager. Let us say Shubham is the manager. And Shubham says, कि, see, finally, जो global clock tree network जब बनाते हैं, तो जो inverters होते हैं, buffers होते हैं, they see 200 femtofarad of load. I have to drive 200 femtofarads. So he characterizes inverters on that. Now what is happening? There is no common language. So what does Global Foundry do at that time? Global Foundry says, okay, there can be 1,000 different kinds of customers that you may have. I cannot characterize on everything. I still need to create a data sheet and share with and benchmark with people. So I will keep for every technology, I will define a particular standard load. For example, an automotive technology, it will say that the standard load is 10 femtofarads. Now, even if Madhav said, नहीं, मैंने तो 5 femtofarad ही देखा था, but Madhav also characterizes at 10. उसने 20 देखा था, he also characterizes at 10. उसने 200 देखा था, he also characterizes at 10. Now, as a SOC designer, I want to choose which offering to use. I know that all the timings are at a standard common load. So at the standard load condition, this is the best compiler to be used. Now, if I put in more load, there could be a change. But at the standard load, this is the best compiler. So that is what you will put in the data sheet. But now just also realize that this guy said 20, this guy said 5, that guy said 200. There is a variety of users. If I just put the same number for everyone, then that 200 वाला तो fail हो जाएगा. इसके पास थोड़ा सा margin बचेगा, but उसका भी थोड़ा सा तो margin deplete हो जाएगा. So what do? Today, characterization is done at the exact condition the user demands. So पहले क्या होता था, चाहे वो मतलब जो लोड्स थे उनका वेरिएशन इतना होता नहीं था. And what you would do was that, okay, just for managing these little variations that could happen in timings because of variations in loads and stuff, let us keep a margin of 5%. It worked. 5% extra margin because, okay, characterization mein inaccuracies hai. Somewhere you will see 10% extra margin. So OCVs, you remember? VDF mein, derating factors and OCVs. So those derating factors were put everywhere. But as we advanced in the technology, we were not able to squeeze as much performance from the transistors as we wanted to. Or the competition became so strong that someone was able to squeeze more, someone was able to squeeze less. And now, if your characterization engine is pessimistic, you are leaving margins, but there is no benefit that is arriving, coming out of it. So the characterization today has become very complex. While for the data sheet, I will continue to use a standard load, but the user will actually get the uh, the characterization or the timings in their .lib at the load value that they want. They know that, okay, in my past design in 65 nanometer, when I designed this chip, there was a load of 200 femtofarads. So I now do 200 femtofarads when I'm doing it at 45. Or whatever scaling factor I may want to apply. 200 ka 180 ho jayega, chahe 200 ka 220 ho jayega. But I know this was the range. So I'm already getting timings for that. Are you able to see this? And not just that. .lib के अंदर आपने देखा है, there is a rectangle, a matrix that is created. That input slope 1, input slope 2, and then what are the timings? Have you seen those matrices? Similar thing would exist for load. So अगर load बढ़ेगा, load कम होगा, तो जो आपने DVD में cells बनाए थे, they are characterized over a range of loads, over a range of input slopes for every timing. Every timing arc is characterized in a very wide range. ठीक है? Now, मैं आपको छेड़ रहा हूं कि आपने पावर पे मोंटे कार्लो करा. पावर पे मोंटे कार्लो कभी भी छेड़ता रहूंगा. लेकिन when we did this, सारा हमने लोड और स्लोप और चीज पे हमने पूरा मैट्रिक्स बना के we made the characterization more accurate. We still realize that we are leaving margins. Why? For the Monte Carlo variations. Because in reality, on the chip, something would run a little faster and would run a little slower. So now there is also this SSTA. Heard about it? Statistical STA? Statistical STA, किसने सुना है? So you did not cover that in VDF. But Professor Puneet Gupta in his talk, even in the DVD class, he talked about it.
So it was a lecture on statistical STA, but he was on the IT packaging and all in the media.
But even in the DVD class, he did mention that SSTA is done and .libs have variations information in it today. Okay. So today, the .libs also have sigma and mean value listed in them. So that I do not need to leave any additional margin for variation when I do my final sign-off. Are you able to see this? Because what happens? एक gate delay होगा तो दूसरा fast भी तो होगा. If there are 20 gates in a particular combinational path, something will go slow, something will go fast. So there's a probability that everything will go slow. That probability is slow raised to power 20. अगर वो slow की probability 0.1 थी कि आपका जो पहला गेट है 0.1 probability से 3 सिग्मा दूर जाता, तो अगर 20 गेट्स हैं तो सारे गेट्स 3 सिग्मा दूर जाएंगे. That is 0.00000000 something 1. That is never going to happen. Are you able to see this? Probability and statistics का कोर्स करा हुआ ना सबने? हाँ? PNS. So it's very useful in semiconductors because by the virtue of that, now you do not need to characterize 3 sigma timings. You don't need to characterize at SS or SS plus 3 sigma. You say, okay, I will characterize that SS typical, SS0 mean, and then for variations, I'm not going to leave anything margins there. इसी के अराउंड थोड़ा बहुत आगे पीछे कर लो, काम चला लो. And I assure nothing will fail. Mathematically, I can assure. Are you able to see this? So characterization engines are fairly complex today. And to be able to do that, now, do you realize that a Mat9 view should have generated that mu and sigma value? Because if Mat9 view doesn't have it, how does the Mat10 view have it? So as a designer, you will have to run Monte Carlo on your designs to arrive at this mu and sigma. Are you with me? So almost all advanced technologies, SSTA is used, and this is what you have to do. Characterization is not just, हाँ हमने एक PVT पे कर लिया, सर एक PVT पे काफी है? No. The PVT that the user says you have to characterize there, and then the sign off will happen. Is this clear? Standard load. कहाँ से शुरू हुए कहाँ पहुंचे? हाँ? Anything else? So tell me one thing. I know that many of you are averse to studying before the class, but after the class, did you watch the video? How many of you watched the video? So अभी तक के सारे आज की क्लास का छोड़ भी दें, अभी तक के सारे वीडियोस यू वॉच? ओके, आज की क्लास का कौन कौन देख कर आया है? Okay, because we are going beyond that. Even after having discussed everything in detail in the class, we are still going far beyond that. ठीक है, आगे बढ़े. So in that class, in the last class, when we looked at the data sheets of, or that data sheet in which there were multiple compilers there, we saw that, okay, there is a CROM and there is a DROM. We told, okay, CROM has a contact programmation and DROM has a diffusion programmation. Incidentally, in that particular thing, there was two compilers, SRAM, SPSRAM and SPSRAM-A. So what were they? They were two different optimizations for a single port compiler. Someone needs a single port compiler. They may want fast access, not worried about area, but another one wants better density, not worried about timings. It can happen depending on application. See, 180 nanometer, the technology when this was done, the data that I showed you was already 25 years old. Okay, 25 years back, VLSI was not as prevalent. Semiconductors were at many places, but not everywhere. Applications were fairly common and understood. But today, semiconductors are everywhere. We are wearing semiconductors on ourselves. Each semiconductor that we use has a different requirement. When you use it in the L1 cache, you want the memory to be very fast. Even in the memory hierarchy, we know L1 cache memory should be very fast. L2 cache, it should be dense, may not be as fast. L3 cache and beyond, okay, still denser, speed we cannot handle. So what that means is that we need to optimize for different, as a designer, we will need to optimize compilers, not just memory instances now, be careful. We'll need to optimize compilers for different purposes. A high density compiler would have a high density memory cell. Because we know high density optimization is required for large memories. Large memories means more number of memory cells. So memory cell is the target. Okay, what is the next thing that uses area? Row decoders. Okay, smaller low decoders. What else? Sense amplifiers. Okay, smaller sense amplifiers, fewer sense amplifiers. Whatever I can do to reduce area, I will do. But when you want speed, you would say, oh, address decoding, let's go for NOR kind of decoding. Dynamic NOR, let the power go to access. But I need speed. Memory cell would be larger current, larger discharge rate, all those things. So every decision then is driven by what is the target goal, and where is that defined? At the MAT5 stage. If you do not do MAT5, if you do not do MAT5 of your compiler, you are definitely going to miss the target because you don't even know what the target is. Is it not? If you do not even know what the goal is, can you reach the goal? You might accidentally, but that possibility is 1 in a million. Is it not? So MAT5 or clarification on what is required to be done should always be brought in first. In the product development lifecycle, we call that as requirement analysis. If you do not do a good requirement analysis, can you build a product? No. Okay. So similarly for low power also. And then we know that there is some 60 cell. We know that for a DRAM there is 1T, 1C cell. But you just open the IEEE website and look for SRAM cells. You would see everything. 60, 70, 40, 5T, 10T, 12T, 19T. Pata nahi. Zero. Each paper selling my is the best. Yes, it is the best, but in that specific use case. In a particular use case, in a particular context, that 40 could be the best. You put that cell elsewhere, won't work. Are you with me? So over here in this slide, RW means this cell allows read and write both. So 60, RW means one read-write port. Now look at the two-port one. First, 81R, one read-write. What does this mean? There are two ports. One port you can only read. The other port you can read and write both. Where could this kind of a memory be used?
A combination of
ROM, you will write something?
only that only for reading, maybe.
I'm saying one port only reads, the other port does read and write both. Where could such a memory be used?
Yeah. There are
Cache.
operations and lesser right. That is close.
Okay, you could think of using this kind of a cell in cache, yes, but that's not the first obvious application that I could think.
Suppose there are two units in a system that one unit can gain the information, but the other unit has to access.
Where does it happen? अभी आपने मुझे ज्ञान दिया कि हमने RISC-V कोर बनाई है. RISC-V कोर अकेले तो नहीं बैठेगी. It will interact with some other circuits in the periphery. The core is operating at one particular frequency or with one particular delay. That periphery circuit, something outside, will operate at a different delay. The RISC-V will be connected to a bus. That circuit will also be connected to a bus. I'm talking about computer architecture. How many of you did the CA course? Many of you have done. So you know there is a bus, different parts would sit on it, and then they would. So there has to be something that would help them do this interfacing. So what you will write from the processor side, but the reading is happening from the bus side. So FIFO, whatever you write first goes out. You need two ports. You could have done with one read and one write port also. But over you have one read and one read-write port so that you can use it both ways. So FIFOs, stacks, all those places, this kind of a cell could be used. What about the other one? The two read-write, both the ports can do both read and write operations.
It might also happen that it's not necessary that one of these frequencies will always be high. They can so then you will need both directions.
You will need both directions, yes. So the pure dual port memories are typically used when you have same data which you want to keep alive and used by two processors simultaneously. So one processor will access from here, other processor will access from there. And you remember we talked about priority thing there, that my state machine could have an arbitration engine in it which says, okay, port A gets higher priority over port B at all times when there's a write happening. That whatever you want to write from port A will be given higher priority over port 2. Similarly, you have multi-port memories, uh, where you may have multiple output channels that could be driven by, let us say, one configuration routing control. मल्टीपल चैनल्स हैं और आप उसके ऊपर एक routing control. So multi-port memories are actually used very, very commonly in these routers. Then ROM, NOR ROM, NAND ROM, then diffusion, contact, metal one, VIA. What is this about? So which programmation layer do you prefer? VIA. Why?
Because the rise market will be till the via point and then
So those of you who have watched the lecture earlier already, you will know that ROM is a read-only memory. You cannot change once it is programmed. Now, आपसे गलती होती है या सब आप perfect हो? How many of you make mistakes every now and then? Okay. You don't make mistakes? You make mistakes, okay. So all of us make mistakes every now and then. So it can happen that we thought this is the code that I want to write in the ROM. Can happen that that code is wrong. हो सकता है? Now, you want to reach the customer fast. You said, okay, ROM code, I will tell you a little later. You just start the fabrication process. Only ROM code I will tell you later because I'm still verifying. Okay. So you start to fabricate the particular chip, wafers of the particular chip, and now you've reached a particular state where ROM programmation has to happen. By now, if your final code is not there, I can't proceed. Things will start to pile up. Huge cost. See, any waiting in any process is a huge cost. आपको ही अगर अपने सपोज किसी चीज के लिए वेट करना पड़ता है, सपोज ग्रेड्स के लिए वेट करना पड़ता है या किसी इट्स अ प्रोसेस, आपको आगे बढ़ना है, आपको अगर वेट करना पड़ रहा है, इट्स अ डेटरेंट. It erodes your profit margins, okay? And over here, there are these piles of silicon wafers which are getting ready, but can't proceed further because आपने अभी तक code नहीं formulate करा. So what happens is that if you are programming at the diffusion stage, then what will the fab do? They will fabricate until P well and well. And then wait, बताओ active कहाँ है, कहाँ नहीं है? So then that is basically they just prepared the wafers and now waiting for you to get to the next step. On the other hand, let us say you had the programmation at M1 stage. So now what they will do? They will not only fabricate the active regions, but they will also do the gate development. They will also do the contact. They will also go to. So VIA1 अगर है तो they will also make metal ones. Now they are waiting VIA1 के बाद. या VIA1 के लिए बताओ what is the mask? What does that do? Now every step takes 2 days. So as a designer, you have got an additional 4 steps, so additional 8 days. And therefore, you can preempt or you can reach the customer a little earlier. Are you able to see this? And time to market is critical. So that is why a higher level of programmation in ROM is desired. Now, suppose आपने सब कुछ यूजर को दे दिया था, आपने सब कुछ फैब्रिकेट करना शुरू कर दिया, आपने फिर से गलती कर दी. Now, the wafers that are being fabricated will start to go waste. If it was a galti or if the programmation is done at diffusion level, then all the wafers which have crossed the diffusion layer are waste. All the wafers. तो entirely पूरी fab खाली हो गई आपकी. But if it was a VR1 ROM, then until Metal 1, everything is still fine. Only the wafers which have crossed the VR1 are failing, need to be wasted. So in those terms also, a higher level of programmation, even when you are running full steam, is helpful. Is this clear? Both aspects. In the first stage, you have more time to design, and the second is that agar kuch galti nikli, to kam lots will get wasted.
So would you say is it impossible to change what is written in a ROM? So if you have contact pins at that level, micrometer level, then
If it's a contact programmable ROM, then no. If it is a VR programmable ROM, then yes.
so maybe from security perspective, our diffusion would be better because it is much more.
We don't know. It depends on how does the hacker try to find out the information there. So आप अगर interested हो security aspects of ROMs के अंदर, so there is this lecture in the YouTube playlist. It's not there in the regular course Cognitrix platform by Dr. Ashish Kumar. You can watch that lecture. It will tell you about how we introduce security aspects into ROMs. Yeah.
So is there any advantage of going to a lower less? Is it like in terms of density? Because then why would these even exist? Why would this? Why would
So yes, there can be advantages. There can be advantages that you need lesser metal layers, or you have more flexibility on the higher layers. You can make things more dense, but there's also a disadvantage. So, in my experience, from what I've seen, earlier technologies, when we only had 3 or 4 metals, ROM D was what people preferred, or ROM C was what people would want to go to because they wanted more metals. है ही नहीं. But today, when we have 10 metal processors, even 15 metal processors or 17 metal processors like that, then people are saying, no, why do we want to go to diffusion-based programmation? I have more metal layers, I can handle it. Things like that. So there was a time when you wanted to do it, you had to do it at diffusion because metals आपके पास थे ही नहीं. If you take metal 1 for programmation, then where will you route your word lines, for example? But today we have so many metals, we route word lines in metal 3.
But if we want the like SPHD kind of cells, where we want the like smaller cells, we want it to be more compact, then we will use the diffusion.
So SPHD is not a ROM.
Oh, sorry. So if
It is a 6 transistor cell.
If you want a compact ROM or more dense ROM,
So for density के लिए you change the architecture first. You go from NAND to NOR to NAND. So density and speed trade-offs you take from the architecture side. Otherwise, it's not much of a difference. In fact, it may happen that because you have a continuous diffusion, now you could be denser when you are VR1 programmable. I don't know. Depends on the DRCs largely.
availability of many metal layers that we program them.
At the highest possible level, yes. So you will see that in advanced technologies, no one talks about ROM D at all. No one talks about it. People say metal 1 या VR1. Contact भी कर रहे हो तो they will be like, अच्छा contact ROM ले रहे हो. Are you with me? That was what we were talking. It depends on the DRCs in any given technology. Area is not usually a variable that changes when you change which layer you are programming in. That's not really the prime driver. The prime driver for area of ROMs, we will see. We will spend some time on ROMs later. There is a lecture on ROMs, so you can watch that also separately. वो Cognitrix में ही है. There is not a strong influence of which layer you are programming on area. Architecture of the cell, whether it is a NAND cell or a NOR based cell, that has a much stronger bearing on area instead. This is important to understand because this will also be useful when we talk about flash memories later. So we talk about it in one of the later classes. You can watch that lecture already. Is that okay? See, that is the advantage of Cognitrix. If you look at the recommended videos on the bottom, it would show you something about the Ramwala lecture when you're watching the lecture on optimization or the memory cells. Because that recommendation engine is about, okay, when you've watched this lecture, you might have a question about ROM. So go to the recommended one. Don't go linearly only. But in a class, I have to still go linearly, however frog I might be. Okay? So then we come to the single port, 60 single port cell. This is the most commonly used cell you will have. You know, we talk about a single port memory, people will assume it to be a 60 cell. That is how common this one is. Okay. But uh, if you just go back, हमने DVD के last penultimate lecture में we talked about how does the 60 cell convert into that. So this is the smallest storage element, SR latch. You remember this? This is the smallest storage element in SR latch. And simply an SR latch doesn't do good to you because you also need to access the memory when there is a clock somewhere. अगर clock नहीं है, तो memory आपके नहीं काम कर रही. Synchronous designs. So there is a sense of clock also somewhere. So what we actually have is, if you want to store some information and access it at my desired time, then what I really need is a clocked SR latch. And over here, I have two signals, set and reset. Like if the user does not handle each of those two signals carefully, my latch could go into a random state. I don't want that. I have only one D. D को स्टोर कर लो, S को जो करना है, R को जो करना है करते रहना. That is what you want. So what you really want is a D latch. Are you with me? Now, if I ask you implement this D latch with the minimum number of transistors, how many transistors would that be? And try implement it, Abhi. There is an inverter, there are two AND gates, there are two NOR gates. So 8 transistors come from the NOR gates, 8 come from the NAND gates. 18 बनता है. आप तो 14 बता रहे हो मुझे. So now you're saying, oh, we'll use something like AYs, what you learned in DVD. Okay, so DVD was not entirely waste if you are going to memories also. So you use complex gates, and this is what you will have. You will merge logic and you will say, okay, NAND, NOR, inverter, सब कुछ को merge करके, this is what I have. This is 14 transistors. All of you can see this? Those of you who have not watched the video in advance, is it okay if we move ahead? I'm telling you, this is what it is. आपने वीडियो नहीं देखा तो आपको कोई बताएगा ही तो, और क्या होगा? वीडियो देखते तो आप खुद कर सकते थे कुछ होमवर्क, बट अब घर जाके कर लेना. Is that okay? Hello? Is it okay? Okay. So now, what is important to realize in this particular cell is that ऊपर देखो, for a memory cell, if I have millions of memory cells placed in an array, if we organize memory cells in an array, we said this would help us do some sharing. So now let us see how does sharing help us. Okay, that's the exercise we're going to go through. If you look at the PMOS side, in a standard CMOS technology, we know that the PMOS has mobility which is smaller than that of NMOS, and therefore you need to size the PMOSs up. This much all of us know. Huh? So, हमें area reduce करना है. Where would we look first? PMOS. Now let us see what is happening on the PMOS side. Now with memories, we also know that the activity rate is very, 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 very low. In fact, CK आता ही नहीं है. हम CK को अगर बाहर से गेट कर दें तो CK आएगा ही नहीं. CK will remain to be zero for a very, very long time. Only when you want to read or write into a memory cell, and there are millions of them, only then you will get a CK. So what is happening? Practically, if CK is almost always zero, what is happening? That VDD is actually coming at the, मतलब ऊपर का जो आपका नॉर वाला जो पैरेलल ट्रांजिस्टर वाला स्ट्रक्चर है, VDD is always available at its base. So there are 4 transistors in this cell which practically do nothing. जो ऊपर था वही हमेशा ही ट्रांसमिट कर रहे हैं. Is it not? Only in a rare case when CK goes to 1, then one of them will transmit, the one will not. Again, even in that case, the other one is transmitting. 4 transistors, those 2 PMOSes, doing nothing. They are the first one you kick out. But as soon as you kick them out, what happens? You are no longer a CMOS circuit. Are you able to see that? If you're not see, CMOS circuit का फायदा क्या था? There are no race conditions. आपने 1 दबाया तो 1 है, वो 1 ही रहेगा. 0 दबाया तो 0 ही रहेगा. CMOS है ना? हाई, वेरी वेरी हाई नॉइज इम्यूनिटी. बट अब आपने क्या कर दिया? आपने उसको CMOS नहीं रहने दिया. Why? Because you wanted to save area. We did that. All of this jugglery circus thing we did in DVD also. Did we not? हमने कहा सूडो NMOS बनाते हैं, डायनामिक बनाते हैं, ये करते हैं, वो करते हैं. जब भी हमने CMOS से डेविएट करा, what happened? We saw that there are some new constraints which will come. Do you realize that? We said pseudo NMOS, we said sizing ratio, we said dynamic, we said charge sharing, we said. So हमने कहीं पे keeper लगाया, कहीं पे कुछ लगाया. We had to do something to handle it because static CMOS is the most robust. You are deviating from it, something will come. So what does come here? That 1 in a million case where 1 was not coming at the base of this parallel structure, now 1 is coming there. So what is the problem then? The problem is that if I now want to write something in that side, now that PMOS is on. I cannot turn it off. Are you with me? That parallel structure on the top was used for write operation to enable that when I want to write into this latch, one side is driving 0, the other side is not fighting that 0. Are you with me? But now the other side is going to fight that 0. But as a designer, you say, I am removing 4 transistors. What it means is I have to take care of sizing. I will take care of it. As a designer, you will take care of sizing. But what you also need to do now is to introduce a figure of merit. You need to check something else. See, अभी तक आप खाली क्या देखते थे? What is the delay? What is the power? Setup time, hold time. Now you've done something else. So now you need to see some other figure of merit also. That figure of merit will have something to do with write. So when we will discuss write operation, notice, keep it in your mind that there is something that is going to come. Are you with me on this? So we removed those 4 transistors. एकदम से कितना छोटा दिख रहा है ना? And then what we did was we just rotated this D and CK वाला जो structure है like this. And we did not just rotate. We also brought clock inside. This is important. Very, very important. Why? Because I will select memory cells with a clock, but I will not select just one memory cell at a time. I will select memory cells which are organized in one particular row or one particular column at a time. So if I want to do any more sharing, then I could probably do that with the clock inside. And what we also notice is that all the cells, so this one, for example, has an inverter which converts D to D bar, and this D and D bar, which are not shared in a horizontal manner, or we are putting it in a different way. Now we put all these, what do you say, 10T transistor cells into an array. And we say, okay, मैं एक रो को एक साथ एक बारी पे एक्सेस करूंगा और एक कॉलम को एक बारी पे राइट करूंगा. So what happens? This D1 and D3 become common because a column has to be written in one go. So what I say is that to access any particular memory location, I will use a crossbar arrangement. This arrangement is called as crossbar. Okay? खाली रो से सिलेक्ट नहीं होता, खाली कॉलम से सिलेक्ट नहीं होता. जहां पे दोनों इंटरसेक्ट कर रहे हैं, that cell is where write will happen. This term is extremely important. This is a standard term that is used in SRAMs, in memories per se. Anyone over here? Okay, no one over here could be doing the neuromorphic memories wala course because unfortunately we did not realize and we had the same slot. But in neuromorphic memories, PCMs and RRAMs and MRAMs, we'll talk about them in our last lecture actually. Crossbar arrangement is used. That is to get more density. कि यहाँ से भी signal आया, यहाँ से भी आया, that particular cell is the one that is selected. So everywhere we are using crossbar to gain more density. So what happens? We say, okay, all these datas, D1 and D3 are actually going to be same. Can I make them common? So I pull that pair of transistors out of every memory cell. Now every memory cell is 8 transistors. This is still not 6 transistors that we were talking about. This is 8 transistors. So now look at it. Over here, we have this D1 driving this particular node to ground. And this CK1 is constant across a row, and this D1 transistor is constant across this particular column. This D1 bar is constant across this particular column. You able to see the mouse there? Yes, you are. So what is happening? Can we do still more sharing? Yes, let's try. So what we do is we make this D1 transistor also common. And what we get is a 6 transistor cell, which is repeated over and over again. But the 6 transistor cell cannot function independently because that D transistor we have pulled out. What is this particular NMOS down there? This particular NMOS becomes a part of the write driver. Reading you can still do, but writing ke liye IO is definitely needed to be able to drive what this common line. So now we start to name these lines. These CKs we call as word lines, and the vertical lines we call as bit lines. And there is a differential pair of bit lines that we talk about. Are you with me? Is this clear? So the simplest storage element was SR latch. We moved to clocked SR latch, but then we had one data bit to store. So why 2 pins to handle? Why waste area by 2 pins? Just one D pin. So data latch. And then we started to optimize by removing some transistors. We have increased complexity elsewhere. We know this. We've not studied that yet. Those of you who have watched the lecture, you understand where it is. It is in the right operation. But we still gained area. And in memories, we said area is diamond. So I am going to do whatever it takes to gain that area. As a designer, मेरी जिंदगी जहन्नुम हो जाने दो. लेकिन area, because that is what brings value to my customer. That is the reason why the user will choose my memory over another person's memory, my competitor's memory. So area is diamond. Same functionality, similar timings, anyone will choose denser. And I want to go to the densest memory cell there. Are you with me? Is it clear until here? Any questions? Great. So This is how our 60 memory cell looks. Now we go to how it operates. So we also done this in DVD. How many of you remember from DVD how does a memory cell operate? So DVD की वो class bunk मारी थी sir. Okay. आज हो तो let's review this again. This is my 60 memory cell, and we know that to be able to read the memory cell, to be able to access the memory cell, I will need to take word line to 1. Are you with me on this? But I do not just take word line to 1 as is. What I say is, before I take word line to 1, I will precondition my bit lines. They will be both pre-charged to a predetermined value. They're saying pre-charged. I'll charge them to a predetermined value before the word line comes. And now when the word line comes, the side which was storing a 0, it will start to discharge the bit line. The other side will not do anything. So we just observe what is the differential, and we say, okay, the side discharging 0, that side we are storing 0, the other side we are storing 1. So this particular cell has 0 stored in it or 1 stored in it. That is your choice. Are you able to see this? This is how the read operation happens. And in the first class, second class, we saw that, okay, this bitline pair will discharge, and then there will be a sense amplifier somewhere else in the IO, it will operate. Okay, all those things you already know. That big picture you already know. Inside the memory cell, something is happening that we just understood. Is this clear? Simple hai? Any questions? Yes. So you say bitline and bitline bar are both connected with an inverter. Where is the inverter over here? Oh, we're not touched the IO region. What we are saying is do whatever, pre-charge both the lines. Don't make an assumption कि वहां पे inverter से दोनों connected हैं कि एक 1 होगा एक 0 होगा. No, no, no. Don't make that assumption. We want a logic. We want an implementation because that is what my memory cell needs. And memory cell is God. Whatever the memory cell needs to function, I have to enable it. Over here, we are saying memory cell needs VDD on both bitline and bitline bar. So even if I'm calling one signal as bitline bar, doesn't mean it is a complement of bitline. I'm calling it for my ease. I'm only calling it bitline bar for my ease. Doesn't mean bitline is a complement of bitline bar. It is not. ये गांठ बांध के रख लो. Because this is something with which your interview will also confuse you. Bitline bar है GB1 कैसे हो गई? No, we are calling it for our convenience. For read operation, we need both to be VDD. For write operation, yes. Now, that's the next slide. For the write operation, what do we do? Even before the word line selection, we say that one bit line will remain 1, the other one will go to 0. यहाँ पे मैंने bit line को 1 पे रखा है, bit line bar को 0 पे रखा है, आप उल्टा कर सकते हो, depending on what you want to write. I did it like this because मैंने जो data लिखा था, I wanted to show you how it changes. If the same data was already written in the memory, I will not be able to show you the change. So I've put it like this. Otherwise, depending on what data you want to write, you will precondition one bit line to 0, the other one to 1. Is this clear? Any questions?
So there is no connection of the inverter from the bit line to the bit line bar. But when we are doing so what the bit lines
देखो will be क्या होगा वो तो भी आपने डिजाइन नहीं करा. You've not designed the right driver yet. As a okay, this thing, ये be very clear about this. As a designer, अभी मैंने प्रोडक्ट डेवलपमेंट के लिए बात करा. First thing you do is requirement analysis. Then you do everything around it to make that requirement happen, make it a reality. Here also, Always look at what does the memory cell require. How we implement it पे मत जाओ. Or how it is implemented. वो गलत है तो गलत है. What do you need? Is it giving you what you need? So you should be clear about what does the memory cell need. That is what I want you to focus on just yet. How we will do it? I'm happy you're looking about how to do it. That's a little too soon. We've not even talked about write drivers yet. You are assuming I will put an inverter between them. I will not. I will drive both bit9 and bit9 bar with a different independent logic. I can do that, na? Where was the inverter needed? Between D and D bar. I never said inverter is needed in B and B bar. I just called them bitline and bitline bar. Just by calling something something, you do not give it the functionality. So those of you who are doing that creativity course, you will see that we will just turn the language around everywhere so that you can. So this language, this. So Sadhguru calls it a conspiracy between two people, not a society and people, two people. I look into your eyes and I communicate something to you. There is a language that we have. आंखों की आंखों में इशारा हो गया, सुना? So language is a conspiracy between two people. And with this conspiracy, we actually create layers of filters around us. Oh, when someone said this, this means this. No. The same word will mean something else in a different language, na? So ये jokes तो बहुत सुने होंगे पति पत्नी वाले कि मैं मोटी लग रही हूं. अब क्या जवाब होगा इसका? हाँ कि ना? लग रही हो कह दिया तो तुम्हें तो ऐसे ही लगता है. और नहीं नहीं मैं लग रही हूँ. नहीं 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 लग रही. अरे मैं लग रही हूँ, देखो यहाँ पे. हाँ लग तो रही हो. हम मोटी लगती रहूंगी बस, है ना? So language is a conspiracy between two people, and we create those filters. We start to perceive things according to the words that are used. So while I'm calling this as bitline and bitline bar, it does not necessarily mean that they are complements of each other. So जो आपने language DC में सीखी थी, digital circuits या BE में सीखी थी कि A and A bar are complements of each other, drop that language just yet. That is a nomenclature that is commonly used, but not here. Come out of that conspiracy now. Is that okay? We want a particular functionality. We will implement that functionality in whichever way we find is optimal and appropriate for the particular memory instance or a particular memory compiler. We can implement that functionality in 10 different ways. Don't bind the designer with implementation. Are you with me? You talk about the requirements first. I want the bit cell to operate like this. For this, I need bitline to remain at 1. Oh no, I want bitline to operate at VDD minus VT. That will also come at some time. So those of you who will go deeper into memories and do some projects, you will see, oh, VDD minus VT पे bitline को रखने से stability improve हो जाती है. So now you just said, I want VDD minus VT. How the designer generates that VDD minus VT is his problem. If they are not able to generate VDD minus VT, they will say, no, this design is not possible. Or to be able to generate, I can generate VDD minus VT, but then you have to give this much area. Are you ready to give that kind of area? Then you will think, oh, I wanted VDD minus VT to reduce my memory cell area by 0.1. But the circuit that this guy is proposing, that will effectively increase the memory area by 0.2. No sense. So, no. You don't do this circuit, I will do VDD. That's a negotiation that the memory cell designer will have with the IO designer or pre-charge block designer. ठीक है? तो सारी लड़ाई झगड़े होते रहेंगे. As a designer, बड़ा मजा आता है. खूब. But always stick to what is the requirement. And don't hesitate to challenge the requirement also. Are you with me? So what do? We take one bit line to 1 and we take one bit line to 0 and keep the other one at 1. And then what happens? The side where the bit line was at 0, to the NMOS, you transmit that 0 inside the memory cell. And as that happens, what happens? The PMOS on the other side starts to turn on. This one now starts to turn on. You were already trying to transfer something from here. And once this PMOS turns on, this at once goes to 1. So what have you essentially done? You have transferred 1 onto the other side and 0 onto the first side. What is important to realize over here is that you, in a 60 memory cell with NMOS pass gates, you always write a 0 first. You cannot write a 1 first because NMOS doesn't transmit 1 as easily. But 0, it can write very easily. This is one thing that you need to realize. And do you also notice that this no longer is a digital 0-1 operation that you thought it would be? मेमोरी में 0 या 1 ही तो स्टोर करते हैं, but you see क्या क्या मजेदार सी waveforms हैं. Go home and simulate any 60 configuration you may just simulate. Open the waveform, see how they are. कुछ भी size रख लेना अभी. Let's see what is happening.
So when we do the write operation, we don't know what is already written on the memory cell, right? So can we do one micro optimization? What if the read operation takes less time than the write operation? There's no possible choices. So if you want to write a file, keep it home. That's all.
Yes, why can't you do that? You can do that. But my experience tells me it wastes more time. But in any other, in a particular condition, in a particular situation, that is what may be required. For example, if you want to make an extremely low power memory and you want to use the advantage of sparse matrices. So, जितने भी हमारे CNNs हैं, they are hugely redundant. Hugely. जितने भी weight vectors आते हैं, चीजें आती हैं, then most of the things are 0. Now, okay, today we have advanced networks or advanced methods to compress neural networks. So itna sara 0 nahi hai, but initially there was a lot of sparsity in it. Okay. Let us say I'm designing a system in which I want to, there's a surveillance camera here and the room is empty. Nothing is moving. So 1 frame, 2nd frame, every frame, nothing is changing. And you say, okay, for this particular security camera, for my computations, all that I need is, has a pixel changed? So all the pixels are, changes across all the pixels are 0. I have a 0 dominating memory. Now, one bird enters into the room. I'm not yet calling a human being, just a bird. So just 1 pixel changes, another. Wherever there are something, so 1 pixel will go to 1, then 1, then 0, 0, 0, 1, 1, 1, something. But remaining entire matrix is 0. Now you want to read. You may want to reduce power of reading 0 somehow. So asymmetric designs में ऐसा आप सोच सकते हो that because you have done so asymmetric optimization, that read before write could be useful, but may not always be the case. It requires a very, and standard memories. What you are suggesting will take much longer to do. Not desirable.
So we can just charge the bit lines. Like if we want to write something, so we can, if we want to write 0, then we will charge that bit line to 0. If we want to write, but that bit line.
Yeah. So what happens? अगर अंदर का flip नहीं भी होना था तो आपने bit line को discharge ही तो करा. जो अब आप कह रहे हो उसमें आप क्या करोगे? आप you will actually read all the bit lines now. Otherwise, you discharge one bit line a little extra, was not needed. So it doesn't really help much from where I see it. But in a very specific, very, very low power architecture, you might have put in some design techniques where it could help. So we can look at that later. Okay. So now what we have done today is we've looked at the 60 SRAM cell and its operation. What we will do in the next class is the figures of merit, the ones that we just talked about, that something is going to change, something is going to become complex now. The next class, we are going to look at figures of merit. I request that please watch the lectures before you come. Okay? It will make it easier for you. All the best. Okay.